Few things are experiencing the rapid technological growth that is occurring in the plastic composite industry today. More and better materials are finding their way into an endless list of uses where extreme measures of durability, reliability, and safety are a primary concern. One of the best examples of this demand is found in the transportation industry. Today, Dorado Bus is at the pinnacle of composite use in ground transportation products. Since 1980, they have produced the highest quality line of light and medium-duty commercial buses for a vast variety of transportation industry users. Larger than the next two competitors combined, Dorado Bus is proud to be the undisputed leader in this segment of the market. Combining the two factors of industry leadership and advancing technology in composites, Dorado Bus decided to go well beyond the required levels of industry standards and testing to assure themselves and their customers that durability, reliability, and safety are at the highest level possible in every Dorado product.
A better informed marketplace increases the level of product quality for everyone. And the basis of this information must be accurate and factual. The best way to assure this is to provide complete documentation and to have the support of an unbiased, well-respected second party. This is why Dorado Bus is proud and pleased to be the first commercial small bus manufacturer to provide you actual footage and documentation of crash testing of both rear and side impact of our Aerotech composite body bus. To make certain these tests were conducted with a high level of professionalism and objectivity, all testing, photography, filming, and data processing was conducted by the capable personnel at the Transportation Research Center in Ohio.
The purpose of these tests was to impact the rear and side of the same vehicle in the same manner it would occur in an actual accident. All equipment, procedures, and testing criteria used was taken from the Code of Federal Regulations Title 49. While there is no specific test requirement for side impact for buses, the information used in these tests was that which was designated for impact relative to fuel system integrity for school buses. The impact at both rear and side was at a 90-degree angle to the body to represent a direct, full-force blow. In accordance with the school bus requirement, the specifications for the moving barrier are as follows: weight, 4,000 pounds, speed, 30 miles per hour, dimension of the frontal area, 24 3/4 inches tall by 78 inches wide. This contour structure sits 12 1/4 inches from the ground. The purpose of these dimensions and specifications is to emulate the most typical vehicle operating on today's streets and highways. To simulate a full passenger load on the bus, 3 50-pound sandbags were stacked in each of the 21 seats. Also, the fuel tank was filled with water. This brought the gross vehicle weight of the bus to a total of 9,670 pounds. First, we'll view the rear impact. We'll observe it at regular speed, and then we'll see it once again in slow motion and stop action. The park brake of the vehicle was set to keep it from rolling a great distance. Obviously, this also caused the vehicle to serve as a more immovable object upon impact. Now let's view it in slow motion and stop action to see how the body reacts to the impact. Typically, the rear of the vehicle moves inward as it absorbs the force of the moving barrier. Upon a closer inspection, we can see a dramatic comparison of how the 14-gauge box steel bumper and the composite body both reacted to the impact. Where the bumper absorbs and retains the energy produced by impact, the composite body structure demonstrates a recoiling effect as it absorbs and dissipates the energy of the impact and attempts to return to its original form. This memory factor is one of the primary characteristics and one of several benefits of a polymer-based material. We can further see that the damage to the rear wall was basically confined to the area of impact. This indicates a minimal amount of shock transfer, which is also typical in a composite structure. A quick inspection of the understructure shows that there is little, if any, disturbance of the body, floor, and chassis frame assembly, which is a further example of the body's flexibility. The same vehicle was then used for the side impact. Our focus in this test is the impact capability of the body structure itself. The specific location of impact on the side of the vehicle allows us to observe a number of important factors. First is the basic impact capability of the structure itself. Secondly is the integrity of the body seam. And thirdly is the integrity of the body-to-floor attachment. The vehicle upon impact is slid sideways approximately 5 feet. As it recoils from the blow, it comes to rest on the impact surface of the moving barrier. As we observed in the rear impact, the composite body's initial reaction to the force is to absorb the energy and basically confine it to the area of impact. As the structure moves away from the blow, you can see the composite material dissipating the energy or recoiling, seeking to return to its previous shape. Close inspection of the sidewall shows where the outer composite panel cracked, but immediately next to it is a body seam that shows no sign of separation. Inside the vehicle, by removing the access hose cover, we can also see that the body-to-floor marriage is virtually still intact. Unlike all other body-on-chassis buses, the unique assembly process used on all Dorado buses provides a continuous 100% bonding of the upper body to the floor. This not only is beneficial in terms of insulation, but as indicated here, also offers a much greater level of safety when impacted. Another impressive result is the condition of the track lock seating system, with the main force of the impact just a few inches below the wall-mounted seat rail. The seat frame mounting brackets remain completely attached with little sign of movement.